Hello everybody, welcome back. We're going to be talking about vectors for the next couple of videos. Now, in my experience, this is the part of the course where students, have to work the least. This is usually stuff that people go, oh, I've seen that before. I had to take physics and I've already seen this. Or I took physics in high school. This is all really old and boring and obvious. So I hope your experience is that this is obvious and easy, because after going through all the stuff we've done so far with calculus, I think maybe obvious and easy would be a nice thing to have to finish up with. So vectors in the plane, two-dimensional vectors are our first stop here. So a vector in R2 means the two-dimensional plane, has two components. If you ask a physics book, they'll mumble something about a vector is something with magnitude and direction, which sort of makes no sense at all. But a vector is something much more specific than that. It does have magnitude and direction, and you can imagine, like you see in physics books all over the place, as an arrow, right, with a terminal point and an initial point. For example, you might have a vector that points from one point, say 1, 2, to another point, say 4, 8. And you might draw a picture, right, where we've labeled the 2 points in the plane this way, and we have an arrow that goes from one to the other, and that's the vector, right? That will take us from the point 1, 2 over to the point 4, 8. And rather than describe it by drawing little vectors around, I mean, we need better notation than that. What this vector really is sort of like directions on how to get from the point 1, 2 to the point 4, 8. And then what you would do is you need to go, well, from the 1 to the 4 in the x direction. So in the x direction, I need to go 3 units. And in the y direction, from 2 to 8, I need to go 6 units. So the vector is, I would write it with these little brackets, right? They're not parentheses exactly so that you can tell them apart from points. But the brackets 3, 6. Right? You've probably seen this written more often as 3i plus 6j. There's nothing wrong with that. We'll do it both ways. I like the little angled brackets better because, as we'll see, you can use ij in 2 dimensions. In a few minutes we'll do k and do things in 3 dimensions. But if you need 4 dimensions, which is perfectly good mathematically, you run out of letters that that work nicely. So you end up writing longer and longer versions with my angled bracket notation. Well, okay, a regular old number, just a number by itself, we call a scalar. You can take vectors and add them. You can multiply by scalars, and the arithmetic works just the way you think it would. So if I had a vector like 3i plus 6j, and I want to subtract or multiply by -1 and then add 5i minus 7j, it works just like the algebra you think it was, like we add like terms, right? You'd have 3i minus 5i makes -2i. And 6j minus -7j, that makes it 6 plus 7, which is 13j. Or written in the notation that I like a little better with the brackets, they look like ordered pairs but with greater than, less than brackets. 3, 6 minus 5, -7, well, you just do it pairwise. So the 3 and the 5 in the first slot, right, get subtracted, and the 6 and the -7 in the second slot get subtracted. If you want to multiply by a scalar, you just multiply through the obvious way if it's written in the I and J notation. With the bracket notation, you would write the 4 times the 3 and also the 4 times the 6. So it multiplies through in each slot. We said vectors will have direction and also magnitude. So its magnitude, the length of that arrow, is better called its norm. And we might use, absolute value if we're just talking about a regular old number to see how big something is. So to kind of use notation that's similar to that, we put sort of double absolute value lines, and those are called something called the norm. So the norm of a vector, like 3, 6, well, it should be the length, and let me draw you a picture. You can pretty easily see what that should turn out to be, right? Because we can do this with the Pythagorean theorem. We've got 3, right, as a length in the x direction, and 6 as a length in the y direction. Not drawn to scale, yeah, this is then how do I find the length of the hypotenuse? Well, it'd be the adjacent squared plus the opposite squared, right? In other words, and that would give us the hypotenuse squared. So square root of 3 squared plus 6 squared. Okay? And when I do the arithmetic, that turns out to be square root of 45. Now, in the homework, you'll see lots of problems that ask you to find a unit vector. So a unit vector has length 1. That's kind of nice because if the length is just 1, then it's really just telling us direction. The magnitude's always 1. So it's a good way to express just direction and not really worrying about what its magnitude is, because we've scaled things so that its length is 1. And to scale things, what we do is we multiply by the right scalar. If the length here is square root of 45, and I want to make a unit vector out of it, I just multiply by 1 over square root of 45. So 3 over square root of 45, comma 6 over square root of 45. That'll be a unit vector. It'll point in the same direction as 3, 6, but if I took the norm of 3 over square root of 45, comma 6 over square root of 45, the 45's cancel, and I end up with a length of just 1. So I feel sort of morally obligated to do something that at least is similar to a physics problem, so that you feel at home doing these sort of vectors. So here's one sort of silly example. If you've seen Muppet Treasure Island, and of course I'm sure everyone has, there are two pirates called Clueless Morgan and Polly Lobster, and at one point they abduct Gonzo, and they tie him up with this sort of ropes around his arms and his legs, and they start stretching him. And unfortunately, it turns out that the Gonzo likes it, and so their attempted torture falls falls flat when they try to torture Gonzo. But let's suppose that they're pulling on his arms with a force of 3,6 newtons and 5,-9 newtons. And again, force is really a vector, as you would have seen from physics probably. So the resultant force, right, would be what you'd get if you just added these two vectors together. So the force on Gonzo is what we get when we add the vectors 3,6 to the vector 5,-9, and altogether we get 8,-3 newtons. So again, most people have seen this sort of stuff in physics, I'm sure, and are going like, yeah, boring. We'll sit there. I sit here and watch this video so far, haven't learned anything new. That may feel like a good thing after all the hard stuff we've done so far. But if you haven't seen any of this before, and I'm going very fast through this, and you're going, I'm completely lost, then be sure to email me. Post a message to the discussion board, and let me know that you need some help, and we can go through this in much more detail if you need to, because again, I'm doing pretty quickly because most people have seen this and they're pretty bored. But if you haven't, then let me know, and we'll go through it in as much detail as we need to make sure that you follow everything. So that finishes up vectors in 2 dimensions. We can do exactly the same sort of thing in 3 dimensions and works just the same way. Every vector will have 3 components, so we might write them as, say, 3, 6, -4 in bracket notation, or 3i plus 6j minus 4k. So we tack on this extra letter. These are like x, y, and z directions. Okay? And of course you can graph the z if you wanted to in 3 dimensions, sort of up and down. When you get to calculus 3, you'll do all sorts of things in 3 dimensions and be graphing things. I hate teaching calculus 3 because I can't draw the silly pictures. I have a terrible time drawing the sort of shapes that you have to do in 3 dimensions. 2 dimensions are more than enough for me. But if you had a 3-dimensional vector and you wanted to find its norm, we do it the same way we did with 2 dimensions. We have the same sort of Pythagorean theorem that works in 3 dimensions. What we would have is the square root of the first component squared plus the second component squared plus the third component squared. In other words, in this example, 3 squared plus 6 squared plus -4 squared. And if we square all those numbers, add them up, you get 61 under the square root for the norm of this vector. You can play the same game to find unit vectors, because if you have a vector and then multiply by 1 over the length, or I don't want to use the word divide because you don't really use that language when you talk about vectors, but you multiply by 1 over the length, then that will give you a unit vector that points in the same direction. Now, one thing that our textbook does is, at this point, brings in the equation of a sphere, just because now we know how distances work in 3 dimensions. A sphere is well, it's a ball in 3 dimensions, and every point is the same distance from the center. So if you had a sphere that's centered at the point ABC, then the equation of this graph would look like we have x minus a squared plus y minus b squared plus z minus c squared equals r squared. If you got rid of the z part, right, and just had the x and y, this would be the equation of a circle in 2 dimensions. So sticking on the z minus c just gives you a sphere in 3 dimensions. So what you'll see in the homework is some examples of this, and the standard kind of question is, here's a graph of a sphere in 3 dimensions. Figure out what the center and the radius is and write it in that sort of standard form, which of course means we have to complete the square. We'll have to go through and take this x squared plus 6x, add something to it so that we can make it x plus something squared. Then the y squared, okay, it's fine like it is because it's already, there's no other y, right? But the z squared minus 5z, we'll have to complete the square there too, right? And then when we add things or subtract things to complete the square, we'll have to balance everything out so that it all works. So let's take this 7 and bring it to the other side as a -7. And when we complete the square, right, well, I've already done it on the screen for us. So I take the 6, of course, in front of the x, cut it in half, and half of 6 is 3. So I'll have x plus 3 squared. But when I write x plus 3 squared, I've added an extra 9, right, to make this work. So if I add a 9 on the left-hand side, I have to add a 9 to the right-hand side of the equation. I don't have to do anything with the y squared. It's already fine. The center, the y coordinate of the center, of course, will be 0. I think of this as y minus 0 squared. But the z part, there's z squared minus 5z. So we have to take the -5, cut it in half. That gives us -5 halves. And when I square that, I get 25 fourths. So I have to add I've added a 25 fourths on the left, I have to add 25 fourths on the right. Right? So if I do the arithmetic on the right-hand side, that all turns out to be 33 over 4. And remember, it's always x minus the coordinate of the center, y minus the coordinate of the center, z minus the coordinate of the center. So my center is at -3, right? That x plus 3 we have to think of as x minus -3. So center's at -3, 0, and 5 halves. And the radius squared is 33 over 4, so the radius would be the square root of that, square root of 33 over 4.